Before I start, I'm going to start with something a little bit more important. This is actually the 10 keys to long life. It's taken from a temple in Kyoto, Japan. It's believed to be over 500 years old. So I'll wait for you to copy them down. Okay, so you may not, some of you may be able to read Chinese. For those of you can't, here is a translation. So these are the 10 keys to long life. You know, you're supposed to eat more vegetables and less meat, have more action and less words. And then the one I've always been fascinated with, the more bathing, less clothing. So I guess if you're a Buddhist monk 500 years ago, you had to do something to amuse yourself. So anyway, hopefully my comments will be appropriate to having you think about what might create long life for kids, a long career for all of us. But if there's nothing else, you walk away with maybe 10 lessons for long life in your personal life. So as Mark introduced me, and just to reemphasize it, I have no medical background. I've been in the software business for a lot of years. As he said, I ran the cloud computing business at Oracle for quite some time, and then started the cloud computing class at Stanford, which is how this whole thing began, which is about 6-7 years ago, a student arrives who has an MD, an MPH, an MBA, and he's chief of pediatric cardiology at Children's Hospital of Orange County. So I know some of you probably know Anthony Chang, but Anthony is kind of my portal into your world. And in some ways, I think because of him, he's inspired a lot of the work that I'm going to go through today. And one of the very first things he told me was a story about a little girl that he was providing consulting for in Myanmar who died on the operating room table. And he said later on, he got to see the echo. They had really difficult time sharing the echo. He got to see it later on. He goes, oh, I could have told him exactly what to do. And I kind of ask a question, which is, well, what if you're a kid in, rural Delaware, rural California, the Shetland Islands, or Rwanda, which, by the way, Rwanda has one pediatric cardiologist in the country. So what if you have no access to a pediatric cardiologist? And so the question I think that obviously Anthony thinks about a lot is, what if we could make computers intelligent? What if we could put Mark's brain, Anthony's brain, Shuby's brain into a computer? So I'm going to take a few minutes here for those of you who have not been exposed to kind of some of the fundamentals of AI and talk about why is it that we've been able to make progress in AI in the consumer space. So some of you may have heard of this. This is actually a project that launched at Stanford now, probably 10 years ago, called ImageNet. It was a contest, it is a contest, to see whether or not computers can recognize images. So you see here that the data set, 14 million images, birds, trees, musical instruments, etc. So the contest began in 2010, and you see here the performance of the computers. So the computers were only, let's call it 28% error rates, or only, we'll call it 72% accurate in 2010. By the year 2017, by the year 2015, the computers were actually better than humans at being able to recognize non-medical images. Now, how did this happen? This is actually a slide that Jeff Dean, who runs Google Brain, uses to talk about the power of neural networks. So I'm not going to do a lecture on neural networks, but please jump into Google, and if you're interested, learn about it. But neural networks have this fascinating property, which is basically the more compute and the more data you throw at it, the more accurate it gets, right? So the more data I throw at it, the more accurate it gets. And if you want a real world example of this, not only must you have large data sets, but you also have to have large, diverse data sets. So, I live in Silicon Valley, and you still see these Waymo cars, vans driving around because they're continuing to acquire data about roads, in this case, obviously. And just to make a point of it, I could build a car that could drive, self-drive in Palo Alto, but let's go try it in Atlanta, and it's not going to work very well. So acquiring large, diverse data sets is key to autonomous driving. And I would also argue key to the world of healthcare and how can we deliver AI algorithms, AI applications in the world of healthcare. But, and Mark already made this point, I'm probably putting a little bit more data to it. There are large, diverse healthcare data sets out there, but it's all digital exhaust today. The back of the envelope I have right now is the average echo lab creates, as I said, about 12,000 ultrasound cases, which is about 11,000 terabytes of data. If all 500 children's hospitals were generating the data, which they are, then that means that in 1 year, we would have 6 million echo cases and a little bit over 5.8 million terabytes of data. Just to give you a sense of this, after 4 years, NIH's IDC project, which is it's called Imaging Data Commons, that was developed to work on oncology for adults, has only hit 40 terabytes. So why, right? So I go, look, at the end of the day, and this is an EU report that was written fairly recently, talking about AI in medicine, AI in healthcare. Their single technical recommendation is we need to figure out how to enable the access, use, and sharing of healthcare data. So the first point I want you to think about is, I don't think the healthcare data is in the EMR or the EHR. I mean, I call it a billing system. It's a great billing system. I understand why we have to have one, but that's not where the data is. The data is sitting in the machines. And back of the envelope, we said there's about 500 children's hospitals. There are about 2,000 healthcare machines. And by that, I mean ultrasounds, MRI scanners, blood analyzers, gene sequencers, et cetera, about 2,000 in a hospital. So 500 children's hospitals, 2,000 machines, that's 1 million healthcare machines. And there's a ton of data I just showed you in an echo lab, just an echo lab. There's already a massive amount of data. The second thing I want you to think about is stop thinking of aggregating data in central repositories. I know everybody's going after doing this, but I'll tell you, there's technical reasons why this isn't going to work, and there's also privacy reasons. So let me talk about the technical reasons. First of all, whenever you try to aggregate data, there's a natural tendency to create a schema or a way to organize that data. The natural tendency is you will do that around a particular application you are thinking about. The problem is when you then try to go use that data on a second application, it's really difficult to do. And this is lessons learned from a lot of years in the world of enterprise software. The second thing, technically, if you want to think about it is, let's assume that we wanted to aggregate all the echoes from all 500 children's hospitals. Okay, that's 5.8 million terabytes of data. Where are we going to put it? I don't know, in Holland? Okay, who's going to pay for the networking cost to get it in and out of Holland? And as has just been discussed, let's go to the third point, which is, well, what about privacy? And I think central repositories, by their very being, they generally go, here, I'm going to aggregate a bunch of data. But if you say, well, what's it being used for? Well, there's no real answer to that. It's like, well, for good things. And one of the fundamentals of privacy is purpose limitation. Central repositories do not implement purpose limitation. So I brought a team together of a bunch of people who have, we've all worked together in the past in different ways to really attack this problem from an infrastructure point of view. And we set ourselves a mission, we call it a moonshot mission, to transform children's healthcare based on access, use, and sharing of data from 1 million healthcare machines in all 500 children's hospitals in the world. So I'm going to take you on a journey of telling you exactly how are we going to go do this. So we have developed a new technology called an edge cloud. So if you took my Stanford class on the very first day, I described Amazon Web Services as Amazon buys 1 million computers, they manage them, they deliver them in an OpEx model, they put them in about 10 data centers in the world. Bevel Cloud, who is the producer of the Edge Cloud service, is fundamentally doing something very similar, getting a bunch of computers, managing them, delivering them an OpEx model. The only big difference is that it's been engineered to go into 10,000 data centers or into Nemours or Seattle or Shriners Hospital, et cetera. There's a bunch of technical things we have to solve to do that, but that's all been engineered as part of what an edge cloud service is. Now, the edge cloud server, this is my little tutorial about what's inside it. Basically, what we've done is we've created a particular kind of application. Remember, I said I want to share data from machines. This application is referred to as a digital twin. We've already built one for Philips, right, which will twin the ultrasounds. In fact, you'll see it in a minute. We'll twin a Lumify ultrasound as well. And when we say twin, we mean it will replicate the data in the machine, to replicate the serial number, the location of the machine, the last error log it threw out, and then obviously the echo itself into what is called edge data services. Edge data services is how we enable very precise data sharing. So the model here is, hey, first of all, that ultrasound on the 3rd floor is Mark's ultrasound. So he's the machine owner. He can decide whether any data is shared, any nomic data, any environmental data. If he says, yeah, I'm glad to share the nomic data and the environmental data, then the next question is, with which edge cloud application? So the application that Laura's building at UPMC, hey, I know what she's working on and I'm happy to share it with her. So I can share with Laura's application, but I really don't trust Tim's application. I'm not going to share the data with Tim's application. So very fine-grained data sharing per machine, per application, which, by the way, just to make a comment about de-identification, it's not, we're taking the data out of the ultrasound. If someone burned into the image, the personal information, it's there. Now you may say, well, that's okay because we're building an application that's just going to be on I was just at MUSC today, on the MUSC campus. That's fine. We're gonna allow that, right? Access to that. We are also developing technology with a third party to actually de-identify that, scrub it off the image at the edge. And now if you want to go take that image and go store it in Microsoft Azure, whatever, go for it. I'm going to talk about another at the end of this privacy mechanism we have developed to be able to do learning while preserving privacy. But that's the fundamental architecture. Just so that you can see one, this is actually a edge server. You can see it over there just underneath that person's hand. It's about the size of your hand. And there is a one-to-one relationship between the edge server and the machine. So it's mounted right underneath the machine. This allows us for infinite scalability, no matter how many machines there happen to be inside what we call an edge zone. We've worked hard to make the install time, Mark made a comment about IT, that the install time is very low. So our goal was installation in less time than it takes to install a Nest thermostat. And we actually did an install a couple weeks ago at an East Coast hospital in 15 minutes. So we're getting this to be pretty simple to go do without a lot of support by anybody. Now, the big thing here is this infrastructure was built to enable the deployment and building of applications. And cardiology applications, orthopedic applications, radiology applications, right? All those applications. So just so you can think about it as an analog, fundamentally what the edge cloud is and Bevel Cloud's trying to do is enable the building of the applications, just as Apple has done that for the iPhone, enabled a whole community of people to go build applications. I'm going to quickly go through a bunch of applications for you to think about. So this is actually a commercial image sharing application by a company called Teleray that will allow you to share images. We're actually going to use it as part of an initiative we're starting called the Emergency Pediatric Network. I keep seeing this problem when talking with clinicians that, you know, just as a example from close to home in Southern California, a little kid went undiagnosed with brain cancer for a month because 2 hospitals and 1 clinic could not share an MRI. A little kid in Phoenix had to be re-x-rayed because they couldn't read the CD-ROM. All this problem can be solved fairly quickly using the technology we've developed. But, you know, obviously we're all interested, or many people are interested in the application of AI. We're working in the area of scoliosis, actually, with a very large hospital and a couple of different alternatives of developing scoliosis applications. We're starting to work in neurology, and just to make a point, and being able to analyze MRI imaging. This is not just built for imaging technology. We can twin a bedside monitor. And so people are developing, we were just speaking with a guy at Texas Children's, sepsis and multiple prediction models out there using data coming from bedside monitors. And just to keep going with this, we have clearly tried to go international on day one. Carnegie Mellon University in Africa actually has a team working on malaria detection off the lowly microscope as another example of an application of the edge cloud. I'll end this little section. Some of you are familiar with Charitha Reddy's work on what's called EchoNet Peds, which was initially trained EchoNet Dynamics on adult data, subsequently is being trained or has been trained on kids data. We'll call it a small number of echoes, etc. We are looking at this as being the bedrock of a I think pretty groundbreaking way of building AI and leveraging the work that many of the research community has done, but also AI while preserving privacy. So it's something we call the Chang method, which I'm not going to spend a lot of time talking about federated learning, but basically the approach is take an algorithm such as EchoNet Peds, deploy it on the edge cloud. Now you can run it in all the different edge zones and determine its accuracy. And then final step, use federated learning, which is a technique that's been developed by Google, Facebook, et cetera, to improve accuracy of, in this case, ejection fraction measurements while preserving privacy, meaning the data never leaves the 3rd floor of Bambino Gesù in Rome. Finally, I have to say, enforce that we designed all this so that we could deploy the application back to the point of care. This is not designed to like write research papers, but designed to go, let's build these algorithms, and now we can go all the way to the point of care. I already told you we've twinned a Lumify machine out there to be able to do this. And obviously, and you're going to hear from Laura, I'm going to try to finish this up. We also can imagine Laura's application being deployed to the point of care and improved continuously using the Chang method. So what does 2040 look like? I'm going to make a comment. It's kind of why I said maybe the future is closer than you think. We, by the end of this year, will have the capacity, and this is probably an underestimate, to access over 100,000 echo cases, probably more than 100,000 X-ray cases. That is over 100,000 terabytes of data from over 100 imaging machines running in 4 continents. We're already, actually, the Edge Zone is already running at Bambino Gesù in Rome. So we went global on day one, and we're actually going to deploy in Africa at Gertrude's at the end of this month. So I'd like to encourage you guys to, make this part of SoPE's mission. I was reading SoPE's mission to collaborate and really just thinking about collaboration, not around PowerPoint or documents, but collaborate around applications. And I know there's so many different things, as I've talked to many of you about, cardiac toxicity, et cetera, which could be approached using these techniques so that we could fundamentally transform healthcare, whether it's in a large city like Beirut or rural Pennsylvania or Vietnam. I'm inviting you to join our Moonshot mission crew. We actually just presented at AI Med 2022. Dr. Reddy was there. Adam Gold, who's the CTO at Chou, Marina Teskova, who's an expert in privacy law, Darren Gates out of NHS, et cetera. I'll leave you with this last comment, which is pediatric healthcare has the opportunity to leapfrog adult healthcare, given the work that we're doing here. And I invite you to be a part of this. And if you'd like to join, I'm in LinkedIn. Please connect with me, or there's my email address, and obviously Shubi and Mark, et cetera, know how to connect. So with that, I know I went a little long. I'll turn the screen back over to Mark and Laura.